recording, so let's go ahead and go through the workbook assignment. So we'll start off by talking about the problems on page 15. I assigned 2 problems from this page. The first one asks you to construct a function based off of the zeros and or provided multiplicities, as well as the degree of the function. So number 1, part A, it provides us with the zeros of -16, 7, with a degree of 2. And what this tells us is that, well, zeros being contributing towards the factors, like we talked about in the polynomial function section, for each 0 that we have, and it does want us to construct functions, so I'm going to use the fancy f of x notation. For each 0 that we have, it gives us a factor. So that's why -16 contributes to that whole factor, and then 7 contributes to this factor. And notice I changed the sign. I'm changing the sign. So -16 in the factor, that becomes x plus 16. And 7 will contribute towards x minus 7. I'm changing the signs in every situation. And the degree of 2 just tells us that if you add up all the multiplicities, which remember, that's the exponents of the factors, which are understood to be 1 and 1 because there's nothing there. It's just saying that if you add those together, you get 2, so it's kind of redundant information. So really the answer is just that. So it's pretty simple. Part B, it goes on to ask for the zeros of 3, and it gives us a multiplicity. A multiplicity of 2. And it also gives us a 0 of 10 with a multiplicity of 4. And then it tells us the degree is 6. So again, the degree is just redundant. It's just verification information. So for each 0 that we have, so 3 and -10, we will get a corresponding factor. X minus 3, X plus 10. But then they go on to give us the corresponding multiplicities. So it said for 3, we get a multiplicity of, or we have a multiplicity of 2, which means for the factor of x minus 3, it simply just has an exponent of 2. And for -10, multiplicity of 4 simply means exponent of 4. And that's it. That's how you construct that. That's what multiplicity means. It's just the value of the exponent. So nothing too crazy. You all might have breezed through this. So that's perfectly fine. Part C. Zeros of -11 with a multiplicity of 3. And additionally 0 with a multiplicity of 2. And it gives us a degree of 5, which again just verifies that the sum of all the multiplicities is 5. So it's kind of redundant information. So again, I'm going to use the fancy f of x notation to make it a function. So for each 0 that we have, there's only 2 of them, negative 11 and 0, we're going to have a factor, corresponding factor. And notice for the 0 one, because some people get tripped up on what 0 being a 0 represents, I'm just going to put x minus 0. That's perfectly fine. I am almost certain that my math lab will still accept that, but I'll show the safe simplification step in a bit. So with the 0 of negative 11, it tells us that the multiplicity is 3. So the exponent is simply 3. And then for 0, the multiplicity is simply 2. But if you want to be safe, because I think that, of course, in the workbook, I would definitely accept that answer. That's perfectly fine. But my math lab works a little bit differently. So if it did require a simplified answer, x minus 0 is just x. So you could just put x squared. And that would be the simplified version. But that is number 1 from the workbook assignment on page 15. So again, I don't expect that one. I don't think that one's too expected to be that complicated. So I guess we shall proceed to problem number 2 on page 15. And problem 2 says graph this function here. And it says graph this function by finding a whole bunch of information. So this is going to seem very similar to a problem you may have seen on the polynomial functions and their graphs section. So polynomial graph aspect. So it goes on to say find the power function and the end behavior and all this other stuff. etc. So we'll find all of these one by one. And then we'll use that to construct the graph. So we'll start off with the power function, because the power function is very, very important. I've mentioned this before. The power function gives us an idea of, so the power function gives us an idea for what the overall characteristic of the function is doing. So here, remember, the power function is found by term domination. If you remember the idea of term domination. So remember, this is whenever you remove redundant or inferior terms and you represent each factor via its dominant term. So this corresponds to any terms that are adding or subtracting to each other. So -1/2 just drops down because -1/2 is not adding or subtracting to anything, but the x plus 1 here, that is definitely an addition, and the dominant term here is the x. X is dominant over 1. So we get rid of 1, we're just left with x. And then x minus 1 squared, the dominant term is x. But there is a power of 2 that corresponds to that factor. So the power of 2 also has to drop down. And then finally, for x minus 2, the dominant term is x. So we have 4 x's in total, 2 x's for the middle one, so that's -1/2x to the 4th. And so that is the power function. And so with the power function, the reason why this is so important is we get a good deal of information from this. In fact, we get 3 immediate things from this power function alone. We get that the degree is 4. So it doesn't really ask for this, but I'm just saying why the power function is so helpful. The degree is 4. The maximum number of turning points has to be 3 then. Remember, that's always the degree minus 1. And then we get the end behavior, which is something we needed. The power function helps us determine the end behavior. And this goes back to those 4 shapes I have in the notes. One of them is faced up like this. One of them's flipped upside down. And then the other 2 are the snake shapes. And so remember, this corresponds to what is the number in the front and what is the parity, or is the exponent even or odd. The number in the front is negative. It's negative 1/2. And the exponent is 4, which is an even number. So the end behavior, if you recall from the notes, is going to be this shape, where there is a gap in the middle, because this is end behavior, not middle behavior. This only tells us what the ends look like. So that's what the power function gives us. That's a lot of important information right there. The degree, the number of turning points, and the end behavior. So far, we have answered, let's see. We need the power function, the end behavior, we got those 2. We need the intercepts next. And the intercepts will help us find some points on the graph that we can physically plot. So that's the power function. Let's move on to the intercepts. Remember, there's 2 intercepts. We'll start off with the x-intercept. Remember, that means set y equal to 0. So whenever we set the function equal to 0, set the whole function equal to 0. And the good thing about this problem, what makes this really easy to find, is that since the function is in a factored form, that means finding the zeros simply means finding the 0 from each factor. So in other words, this factor gives us an x-intercept, or a 0 of -1. This one gives us +1. This one gives us 2. So those are the zeros of the problem. But remember, the zeros and the x-intercepts are the exact same thing. It means the same exact thing. It's just different wording. So we have 3 x-intercepts now that we got from each factor. So I'm going to write down these intercepts. Let's see. -1, 0. So I'm writing them down as ordered pairs. These are points that we can physically plot on the graph whenever we get to that part. So -1, 0, and then 1, 0 because we found a 1, and then 2, 0 because we found a 2 as well. So those are our x-intercepts. And we can additionally find y-intercepts by setting x equal to 0. So I replaced every x with a 0. If you plug all of that into your calculator, you should get +1. You will get +1 if you plug all of that in your calculator. Which means that gives us the last intercept, the y-intercept of 0, 1. So we have the power function, we have the intercepts. Finally, all we need is the behavior near each x-intercept. Sorry. The behavior near each x-intercept. So remember, we found 3 x-intercepts. Here, here, and here. We found 3 x-intercepts. And what the problem says is we want to figure out the behavior near each x-intercept. So the behavior means we need to know the multiplicity. So remember, the multiplicity is the exponent of the factors. So with that being said, we'll start off with the -1 on the far left here. The multiplicity, I'll just put multi for multiplicity. Remember, that corresponds to the exponent of the factor that it came from. The exponent is understood to be 1. 1 is an odd number, which means that here, the behavior is that this would cross. This is the thought process you need to have with behavior near each x-intercept. And so with the +1, same idea. What's the multiplicity? It's the exponent, which there is 1. It's right here. It's 2. So 2 is an even number, so this would touch. And then finally, for 2 here, what's the multiplicity or the exponent of the factor? It's understood to be 1. 1 is an odd number, so this would cross. So now we have all of the pertinent information here required to graph this function. So let's go ahead and set up the graph, and there should be one provided for you in your workbook. Let's see, 1, 2, 3, 4. Okay, so let's go ahead and plot definitive things. The intercepts. Those are definitive points that we could plot no matter what. First one is -1, 0, 1, 0, and 1, 0, and then 2, 0, and then 0, 1. So there are the 4 points right there. Another thing we can utilize is the end behavior. Remember, we found the end behavior up here. What does the end behavior tell us? It tells us what's happening on the left of the graph and what's happening on the right of the graph. So in other words, it tells us that the graph will come up from this side to touch the furthest point on the left, and then would come up from this side to touch the furthest point on the right. So notice how I'm taking those 2 sides of the end behavior and I'm attaching them to the leftmost point and the rightmost point. So that's generally how the end behavior is applied. And now we need to figure out, well, as we slowly start to trace and connect all the dots, we also need to utilize the behavior near each x-intercept. Will it cross through or touch? So this here, this is that x is equal to -1, and we said this crosses. We said that over here. So that means the graph will cross through the x-axis, come up and touch this point, but we also need to start curving down to touch the next point. So just like this. Now the question is, what happens there? What happens at that point? This is x is equal to +1, and we said that touches. So instead of the graph going straight through, it will bounce off. And then we have to connect the next dot. And this makes sense that the graph crosses through because we said for the final one, it does cross. So this would be how you construct the graph. So as you all probably know, the workbook pages are more difficult than MyMathLab. So in MyMathLab, generally what will happen is, so in MyMathLab, what they do is they'll give you, or they did give you for this problem, multiple choice, and you pick the correct graph. And you'll see this as well in the next homework section as well. So you are not required to graph these by hand, except for the workbook. So I just wanted to give everyone that update if you haven't already seen that from the homework. So that is the, so that concludes page 15 of the workbook. So that's everything you would do for problem 2 there. So let's go ahead and extend the page and move on to page 17 because I assigned 2 problems from page 17. Page 17. Start off with problem 1. And it gives us a function and it wants us to determine the domain, the intercepts, and the equation of the asymptotes. Now, page 17, this corresponds to not polynomial functions anymore. So this pertains to what's called rational functions. So rational functions, well, from the video I explained on rational functions, it's a polynomial divided by a polynomial, as we see here in the construction of problem 1. So with this problem here, what you may notice in the homework is they may ask you to put the rational function. One of the first things they ask you is put it into a factored form. Sometimes they ask for that. Sometimes they don't. I'm pretty sure they do for the majority of them. But one thing I want to do is put this into a standard form. Now, how do you put a rational function in standard form? Well, how did we put a polynomial function in standard form? We had all of the exponents in decreasing order. So here, for rational functions, it's put the numerator in standard form and put the denominator in standard form. The numerator is already fine because the exponents are going in decreasing order. The dominant terms are the leading ones. But the denominator, I'm simply going to switch the x and the 3. That's it. I just switched them. And that is standard form because x is dominant over 3. So I'll put x in front. This is going to be helpful later on. It's important to acknowledge this for rational functions. This is helpful for finding what's called the horizontal asymptote, as we will see momentarily. So, with this being said, let's go ahead and find the domain. So the domain of a rational function, and this is going to be true throughout the whole section, rational functions have denominators. What's bad about denominators? They could equal 0, and we cannot divide by 0. So naturally, it makes sense to set the denominator not equal to 0 and solve for x, because we don't want to divide by 0. So if you remember that, then you simply get that the domain is x cannot equal -3. And that's it. And you can leave it in this form. That's fine. This is an inequality form. So we find the domain, and it also turns out that this 95% of the time, this will immediately tell us what's called the vertical asymptote. We can immediately find in 95% of cases the vertical asymptote based off of this. Notice the only difference is the sign. Only difference is the sign. Notice for the domain, I used a not equal sign. And for the vertical asymptote, I'm using an equal sign. That's the only difference. And this will be the case in 99% of your homework problems. I'll talk about the other case on Wednesday. So I'll talk about that other case on Wednesday. But most of the time, this will always be true. So that's something we'll keep in mind when we get to the equations of the asymptotes part later on. Let's move on to the intercepts. Well, there's two types of intercepts. There's x-intercept, of course. And we'll go ahead and prepare the y-intercept. This one's set y equal to 0. This one's set x equal to 0. Okay, we'll start off with the x-intercept because we set the whole function equal to 0. And I'm going to go ahead and use the standard form for now on. So I'm using the standard form, which just means the denominator is slightly changed. We switched the terms. But now we get here, and the goal is to solve for x. So how we can simplify this, we can cross multiply or just equivalently multiply both sides by the least common denominator of x plus 3. I'll go ahead and just view this as a cross multiplication, which would give us 0 times x plus 3 is equal to 3x plus 6. And 0 times anything is 0. So it simplifies really nicely. And solving for x, it's not too much of a leap. So that x is -2. And so that gives us our first intercept. Found -2 for x, and that was when we set y equal to 0. And now for the y-intercept, we set x equal to 0, which just means every x now becomes equal to 0 as such. And this is just 6 over 3, which is 2. So we find another intercept. When x was 0, y is 2, just like that. And so we found two intercepts, which are two definitive points that we could plot on the graph of the function when we get to that part. So we have the domain, we have the intercepts. Finally, we need the equations of the asymptotes. Now here, we already have one of the equations of one of the asymptotes, because there's two asymptotes. And if you have no idea what I mean by asymptotes, this is something I talk about explicitly in the rational functions videos, probably more so in depth in the graphs of rational functions video. So if you have not seen that video, this is a good, initial understanding of what's going on. But I'm going to visualize asymptotes fairly soon. So we already found this vertical asymptote here. That's one of the asymptotes. Remember, vertical is up and down. So we're going to utilize that when we construct the graph. Now we're going to find another asymptote called the horizontal asymptote. Naturally, horizontal, the horizon, it goes left and right. So now the question is, how do we find that? So in the video, I do mention 3 criteria for how to determine the horizontal asymptote. And all of these criteria, you pick one depending on how the degree of the numerator and the denominator correspond to one another. So what I want to do, I'm going to go ahead and rewrite the function down here. And the reason why, so I mentioned earlier, we want to put this rational function in standard form. This isn't factored form, it's standard form. The reason why is because it helps us determine an appropriate choice for the horizontal asymptote. If you don't put the rational function in standard form, you might not get the correct horizontal asymptote. So that's why it's important to have the rational function in standard form. And so here we need to figure out the degree of both the numerator and the denominator separately, as if they were their own polynomial functions. Now remember, the degree is the exponent of the highest term after we put it in standard form. Hence why this form is important. The degree of the numerator is 1 because the exponent of x is 1. Same with the denominator. So what this means, since the degrees are the same, the horizontal asymptote I have this in my notes for all 3 of the 3 conditions: when the numerator degree is larger, when the denominator degree is larger, and when they're both equal. This one is going to be the ratio, well, is the ratio of the leading coefficients. It's the ratio of the leading coefficients. So what does that mean? Well, ratio means fraction. Coefficients mean numbers in front of the variables. So in red, I will illustrate this. It's going to be 3 divided by whatever the leading number is, not variable, the leading number, which is understood to be 1, which is why I have a space there. So the horizontal asymptote it's normally y is equal to, because sometimes they'll ask for it as an equation. It's going to be 3 over 1. Because it's the ratio of the leading numbers. 3 is the number in the numerator, 1 is the number in the denominator. But of course, this simplifies to just y is equal to 3. So that is the horizontal asymptote, which is y is equal to 3. Again, if you see my video, you will also see me talk about this and do problems that pertain to this process. And here's another look at it. So we have found a whole bunch of information, and we're going to use all of this information to, we're going to use all of this to plot the graph. Now, you are not responsible for plotting this by hand, because like I said, in my math lab, generally what they have you do is pick the correct graph from a list of multiple choice options. But if you are curious, as well as you have to do this for the sake of the workbook problem, this is how these graphs are derived. So if you were taking this class, if this was a paper class, you would be required to graph this as such. And I'm pretty sure in your workbook, they go by increments of 2. So it would be 2, 4, so on and so forth. So the first thing we can plot are any definitive points we have, which are the intercepts primarily. We have 2 intercepts, -2, 0 and 0, 2. So -2, 0, 0, 2. Remember, these go in increments of 2s. So something else that we can put on here, the horizontal and vertical asymptotes. Generally, these are illustrated. Most of the time, they're illustrated as these red dotted lines. We have a vertical asymptote of x is equal to -3, where verticals up and down. -3 is right here. And then the horizontal asymptote is y is equal to +3. So those would be the asymptotes. These act as barriers, so the graph can't cross through them. And in particular, if we have to connect the dots no matter what. And for any asymptotes, the graph always gets exceedingly close to the asymptote, but never quite touches it. Just forever gets closer and closer and closer. Doesn't quite touch it. Now, the final issue, it doesn't really show up here. It'll be more obvious when you have the multiple choice selection, is that we only filled out the right half of the graph. We didn't fill out the left half. And the reason we naturally filled out the right part of the graph is because we had intercepts. There's still a left part of the graph. And intuition would say that, well, we can draw the graph either up here or down here somewhere. But which one? You could try to use logic to say, if we drew the graph down in this area, then we would have another intercept, which means we would have found it. But we did not find an intercept. So that means the graph would have to be up here. And graphs always sort of, they will smooth out near these asymptotes like I drew it. They always do that. But another thing you can do, since this is multiple choice on MyMathLab, you could pick a test point. So if you picked, this would be, for example, -6. If you plug in -6 for x, what kind of number do you get? It turns out, let's see, when you plug in -6 for all the x values, -18, that's -12, and then -3. So you get 4, get +4, which would be a value right here. So it tells you exactly where that side of the graph would have to be. But this would be your graph for that function. And this would be how you would derive it from scratch. Okay, so finally, we have one more problem. It's just problem 2. And I did want to check one thing. Yeah, there's one thing I wanted to check here before I do this problem. So just give me 1 second here. I'm sorry, I'm not down. Unit, oh, to the left. Okay, so yeah, I wanted to make sure to see how they did this problem because it'll save us a little bit of work here. And I'd rather tailor this to how this problem goes. So as you can see, and I'll talk about this more on Wednesday's session. On Wednesday's session, I'll go through this section of homework problems. Today's just primarily workbook. But yeah, so really the question in the workbook that I'm about to go over is exactly like this problem here, number 18 in the homework. And I want to kind of knock out 2 birds with 1 stone here. So this is viewing the problem as a transformation problem. So I'm really going to look at the problem as such. So this is number 2 from page 17 of the workbook, but it's also very similar to number 18 from the homework, as you just saw. It's very similar to number 18. It's almost the same function. So I'm going to be following that pretty religiously. So the function in question and it still wants us to find the domain, the intercepts, the equations of the asymptotes, and then ultimately graph it. So the way I'm going to do this is I'm going to follow this just like it's the example up here. And I suppose I'll just go ahead and start it over so we can follow it in order. So with this problem here, what they're doing is they're saying that this problem here is a transformation type problem. And you might notice this because there's a number added to the x directly, and then there's a number subtracting the function as a whole. So really, we can identify this as if it were a standard transformation problem, you know, stuff from the previous sections that we've talked about. The -3 means we're going down 3. The +2, since it's adding to the x directly, this means we're going to the left 2. And then the negative in the front, if the whole function is negative, this means we reflect about the x-axis. So I'll just put that disclaimer. It's very much like number 18 from the homework. So we have all of these things, and this is transforming. So you might be wondering, so what's the initial shape? Because this looks like a mess. What does the initial shape look like? And thankfully for us, in the way MyMathLab constructs everything, once we do figure out all the transformations, so let's see, down 2 units, reflect across, what did I say, the x-axis, and shift 2 units to the left. Okay. All right, so all of these graphs tell us the shapes. All of these tell us the shapes. We can all see that it's just one shape, it's just shifted in various ways. So if anything, we know that the shape, just from process of elimination, or not even that, just from the consistency of all the options, that the shape is something like this. So that's what the shape is like. Maybe not perfect in my illustration, but we can all see that that's the shape. And so we need the shape to conform to the transformations. So one of the things we said was there's a reflection about the x-axis, which does give us the ultimate shape. Initially, you would flip those back up to see what the original shape is like, but we need to make sure that this shape here goes. So what were the two shiftings? It's left 2 and down 3 for our problem. It's different for this problem, but in our problem, it's left 2 and down 3. So really the graph, so we can go ahead and construct the graph now. So it's saying in the original shape, there's asymptotes here and here. Those asymptotes will shift accordingly. So if we go to the left 2, 1, 2, then the asymptote shifts as such. And if we go down 3, 1, 2, 3, well, guess what? The asymptote shifts as such. So this will now be at x is equal to -2, and y is equal to -3. And from here, we know what the shape looks like. So all we have to do is just draw it in. So if I draw this asymptote out a little bit further, the shape, because all the options have the same shape, we just need to make sure that the shape lines up with the shifting that we apply. So for this problem here, we said it's to the left and down. For this problem here, we have exactly that. So from here, we can go ahead and figure out the domain. Again, we're just going off of how this problem orients everything. Just knock out 2 birds with 1 stone. So it's asking for the domain next. We can use the graph to help us determine the domain. So remember, the domain is left to right. So to the left, we start off coming from -infinity, but then we hit this issue. We hit this barrier here. So we start off coming from -infinity on the left. And they do want this in interval notation, so I'm going to go ahead and prepare for that. So it's coming from -infinity, just fine. And then it stops at this barrier. This barrier tells us, all right, x can be everything, but not -2, because that's where the barrier is at. And notice I use parentheses because there's a barrier there. If I didn't use parentheses, then that means we would be able to equal -2. That wouldn't be a very good barrier. But we're not done because I didn't highlight the whole graph. I have to use that union thing because now we skip around -2. So we start with -2 as the frame of reference. And now we go all the way to the right and we see that we can go on without any issue. So this would be positive infinity. So that would be the domain. And equivalently, I can go ahead and fill that out in the homework question as well. So the domain for this problem, well, the graph was exactly this. It actually turns out to be the same thing. And although it doesn't ask for it in this problem on the workbook page, I'm going to go ahead and find the range. Oh, and also the equations of the asymptotes, because the workbook does ask for those, we already have them here. So we actually already have the equations. We have them here, here. And yeah, although the problem doesn't ask for the range, I'm just going to go ahead and put it anyways. The range here, remember, that's lowest, highest. So the lowest we can go is to negative infinity. So we can go ahead and start off our range with the lowest, which is negative infinity. And then it slowly climbs up. And then it starts to level off because we hit another barrier. So what's the highest that we can go? Well, where does the barrier make us stop at? Y is equal to -3. So the barrier says you cannot go any higher than -3. And we ask, well, can we skip around the barrier and continue on like we did for the domain? And the answer is no, because there's nothing going on up here, nothing at all. There's nothing going on up here, so our range would stop right there. So the range is just negative infinity to -3, because everything is forced to be below that horizontal asymptote. And for this problem, we would resemble that the same way. This is the graph. The highest we can go is to the barrier from negative infinity to, so what did I say, -2. Now, for the sake of the workbook problem, I will go ahead and detour a little bit from the MyMathLab example, because to finish the workbook problem, we just need to find the intercepts, and then we're done. And the MyMathLab problem is not asking for the intercepts. It wants increasing and decreasing intervals. So let's go ahead and finish the workbook problem by finding the intercepts. And there's two intercepts, the x-intercept and the y-intercept. So when we set y equal to 0, what we're doing, setting the whole function equal to 0, and we're going to solve for x. So what we can do, add 3 on both sides. 3 is equal to -1 over x plus 2 quantity squared. And we can cross multiply as well. Now you might notice something interesting about this spot that we're in. We could technically stop right here for the x-intercept, because what I'm noticing is a square. We're squaring a function or an expression, and then the output's a negative number. Another way to see this is if we divide 3 on both sides, then we would want to apply. So if we divide 3 on both sides, we would want to apply the square root on both sides, using the square root method, as it's called. But the problem is, when we apply the square roots, we're taking the square root of a negative number. That's not good. So we do not, the conclusion is we do not get an x-intercept. because all of this was in the pursuit of finding an x-intercept. So when we tried to find one, we hit a contradiction. We hit an error. So we don't get an x-intercept. So we ignore that and we move on to the y-intercept. So we set x equal to 0. All the x's equal to 0. This is negative 1 over 0 plus 2 squared minus 3. And we can solve this pretty quickly. That's going to be negative 1 over 4 minus 3. And that is equal to, that's going to be negative 3.25, which I think is negative 13 over 4. Okay. So we do get a y-intercept. When x is 0, y is negative 13 over 4. And I'm going to also provide the decimal approximation, because now we're going to graph, well, we don't have to graph this whole thing because we already have the graph here. But if we were to include this point on the graph, x would be 0 and y would be negative 3.25. That point on the graph would be right here. Because it's a little bit further than the negative 3 for y. Negative 13 over 4 is negative 3.25. So just a little bit further. And so that would conclude the workbook problem. We found the intercepts, which there's only one, and we plotted it on the graph that we already have. And just to finish up MyMathLab version of this, because we did have this concurrent MyMathLab session up, and all we have to do is find increasing and decreasing. So I'm going to do that for this problem. Now that we know the graph, I'm going to go ahead and find the increasing and the decreasing intervals, because this doesn't involve any computation, it's just analyzing. And this will help you with number 18 from the homework, and probably other ones as well. So increasing means that from left to right, you are going upwards. You are decreasing here, that I'm drawing in black right now. That is decreasing. You're going downwards the whole time. And then the next part I'll highlight in blue. This is increasing. You're going upwards from left to right. So we need to denote those intervals using the x values. So what are the x values of the things I just drew? So the decreasing part that is in black, that's negative infinity all the way to negative 2, because that's where the barrier's at, is that x is equal to negative 2. So it's decreasing from negative infinity to negative 2, and then it's increasing, where I'm highlighting this in blue, that's from the barrier, starting from the barrier, which is negative 2. That goes all the way to positive infinity. So equivalently, on the MyMathLab example I have pulled up, actually it ends up being the same thing. It's just a coincidence, though. So That's a workbook problem right there, and a My Math Lab example as well. So number 18 from the homework. So two birds, one stone. So does anyone have any questions about that? Because if not, that's all the workbook pages. The workbook's due tonight, so if you stuck around, then you can check what I have with what you jotted down, or maybe you can jot it down for all I care. But go ahead and turn that in. If you have any specific questions, let me know. We have about 10 minutes left. But other than that, that's all I have on my end. Have a good day.